I'm going to present the mirror module of Avidian SafeKit in detail, including how to configure the restart scripts, the internal parameters in userconfig.xml, and its operation with various state transitions according to failures. Let's start with an overview. Let's examine how a mirror module works and the associated states and colors in the console. At step 1 in the figure, the mirror module is running in the prim second state. The application runs only on the prim server, and the virtual IP has been set on its network interface. Only modifications made by the application inside files are replicated in real time. At step 2, the mirror module has been stopped on node 1, or node 1 has experienced a failure. This triggers an automatic failover to node 2. The module is now in the alone state on node 2. The virtual IP has been set on its network interface, and the application has been restarted. There is no more replication from node 2 to node 1. At step 3, the mirror module is restarted on node 1, and node 1 resynchronizes its local folders from node 2. During this resynchronization, the state is second and the color is orange on node 1. The application continues its execution on node 2 in the alone state. At step 4, the data has been resynchronized, and we are in the second prim state, ready for a failover. If you prefer the application to run on node 1, you can stop the module on node 2. This will trigger a failover and a restart of the application on node 1. You can do this manually through the console at an appropriate time, or automatically just after the resynchronization, by configuring the default prim parameter in userconfig.xml. Let's present to you the various solutions that you can implement with a mirror module. Firstly, for a new application on Windows or Linux, you can utilize the mirror.safe module. We offer a comprehensive list of SafeKit solutions on the Avidian website, all available with a free trial and a quick installation guide. Secondly, our pre-configured solutions for Windows include SQL Server.safe for Microsoft SQL Server, PostgreSQL.safe for PostgreSQL, MySQL.safe for MySQL, Hyper-V.safe for Hyper-V, and more. Thirdly, our pre-configured solutions for Linux include Oracle.safe for Oracle, PostgreSQL.safe for PostgreSQL, MySQL.safe for MySQL, KVM.safe for KVM, and more. Fourthly, once deployed, the configuration files are available in the modules directory of SafeKit. If the module has been deployed with the name AM, then you will find an AM subdirectory. Inside AM/bin, you will find the restart scripts named startprim and stopprim. And inside am/conf, you will find the userconfig.xml file. Let's start by explaining the startprim and stopprim scripts. Let's begin with high availability at the application level. The startprim and stopprim scripts are used to start and stop an application. In this solution, you need to install the application with the same settings on both nodes. Additionally, you need to configure the clients to connect to the virtual IP address, which will allow seamless failover in case of a node failure. Next, let's discuss high availability at the virtual machine level. The startprim and stopprim scripts are used to start and stop a virtual machine. In this solution, place the critical application inside a VM and configure the clients to connect to the physical IP address of the VM. There is no need for a virtual IP address in this case. The physical IP address of the VM will be rerouted when the VM is restarted on the secondary node. Now let's talk about automatic boot. Remove the automatic start at boot of the application or the VM. This start will be managed by the automatic start of the module at boot. To do this, configure the SafeKit module to start at boot by adding boot equals on in the service tag of the userconfig.xml file, or by using the SafeKit boot command. Let's now explain how to log messages from a restart script, either in the script log or in the module log. As shown in points 1 and 2 on the slide, all output messages of startprim go into the script log. Thus, for debugging purposes, you can write specific messages in the script log just with the echo command. More generally, you will find the outputs of service startups and stops in the script log, along with any potential error messages that can help with debugging. As shown in point 3 on the slide, by using the SafeKit print command, you can log a message in the module log. As shown in point 4, when executing a command like the stop one with the -i startprim option, you will have a stop message in the log, indicating that the stop action was initiated by startprim. Let's now examine in detail the userconfig.xml parameters that can be configured for a mirror module. Here is an overview of the userconfig.xml file for a mirror module. First, you have the heartbeat section defining the networks through which heartbeats must pass. Then, you have the virtual IP configuration. Next, you see the real-time replication and the path of folders to replicate. Following that, you have the user tag, which enables the execution of restart scripts. The three other tags on the right of the slide concern checkers and are explained in the checkers slides. Let's detail the heartbeats configuration. Heartbeats synchronize states and actions between two nodes through the network. There is an automatic failover when all heartbeats are lost. The heart tag allows the configuration of heartbeats in userconfig.xml. The pulse attribute defines the delay in milliseconds between two heartbeat sendings. The timeout attribute defines the maximum time in milliseconds before considering that heartbeats are lost and triggering a failover. In the heartbeat tag, the name attribute is the name of a LAN defined in the cluster.xml file. Here, two heartbeats are defined on the default and private LANs. The IDEN attribute is particularly interesting. If you assign it to the flow value, it designates the network that will support the replication flow. If no flow value is set by default, the replication flow will be on the network of the first heartbeat. The IDEN attribute is also used for naming resources. In the example, heartbeat.default and heartbeat.flow will be the two resources giving the status of the two heartbeats. Finally, you can set as many heartbeat tags as you have network connections between both nodes. Let's now detail the virtual IP configuration. A virtual IP address, also named VIP in the figure on the right, is a third IP address coming in addition to the two physical IP addresses of the two nodes. In a mirror module, the virtual IP address is set as an alias on the network interface of the primary node, which runs the application. Both nodes must be in the same subnet to be able to switch transparently the virtual IP address from one node to the other at the MAC address level, level 2 in the network layer. Clients, as presented in the example, are connected to the VIP. When the prim server is node 1, the VIP is associated with the Ethernet MAC address, one of node 1. This mapping can be viewed in the ARP cache of clients. When node 1 fails, SafeKit automatically sets the VIP as an alias on the network interface of node 2 before restarting the application. Then, the ARP cache of clients is updated with the mapping of the VIP to the Ethernet MAC address 2 of node 2. Thus, clients are reconnected to the application on node 2. The virtual IP works with Ethernet interfaces in teaming, bonding, VLAN, and IPv6. Virtual IP addresses are configured in the VIP tag of userconfig.xml as presented in the slide. The check attribute set to on in the interface tag means that a checker will detect interface failures. As shown in the text box of the slide, a resource is associated with this checker, and the action taken on interface failure is to put the module in the wait state. Virtual ADDR is the tag where the address or DNS name of the virtual IP is set. It is preferable to configure an IP address to be resilient to DNS failures. You can set here an IPv4 or IPv6 address for the virtual IP. One-side alias means that the virtual IP address will be set as an alias of the physical IP address on the network interface. It also means that if the primary node initiates a connection to an external device, then this connection will start with its physical IP address. In some cases, it may be useful to initiate connections from the primary node with the virtual IP. In this case, you can set one-side instead of one-side alias. The check attribute set to on in the virtual ADDR tag means that a checker will detect duplicate VIP address conflicts or removals. As shown in the text box of the slide, a resource is associated with this checker, and the action taken on error is to stop and then start the module. Finally, you can set several virtual IP addresses on the same network interface by replicating the virtual ADDR tag. And you can also replicate the interface tag to set virtual IP addresses on several network interfaces. We consider now two nodes that are in two different subnets. This is particularly the case when implementing a high availability solution in public cloud infrastructure like Azure, AWS, or GCP. SafeKit nodes are put in two different high availability zones, which are in two different subnets. In this case, the VIP tag must be removed from userconfig.xml, as the rerouting at the MAC address level is no longer possible. Instead, the virtual IP must be defined at a load balancer level. The load balancer must be configured with the physical IP addresses of the two nodes, and with a health check to route the traffic to available nodes. SafeKit offers such a health check per module by answering to a URL with the ready.txt file. If the module is prim or alone, the URL returns OK. If not, the URL returns not found. Thus, the load balancer routes the traffic to the primary server, where the application is running in the mirror module. In the text box of the slide, you have to replace AM in the URL by the name of the module. Note that the application must support this configuration with clients connected on the VIP of the load balancer, and with the application receiving connection from the load balancer on the physical IP address of the primary server. There is another solution not explained in these slides, which consists in rerouting at the DNS level. But this solution is not working in most cases, because the prerequisite is that clients makes a DNS resolution after a failover to be rerouted to the new server. Most often, they do not and continue their execution with the IP address resolved when they started. Moreover, the time to propagate a DNS rerouting can vary, but typically it takes a few hours to up to 48 hours for the changes to fully propagate across the internet. Let's now detail the real-time file replication configuration. Let's begin with the prerequisites. Firstly, it is important to ensure that the replicated directories are located at the same location on both nodes. Secondly, it is better to exclude certain types of files from replication, such as binaries, temporary files, and OS files. Thirdly, if antivirus scanning is incompatible with the replicated directories, it should be disabled. Fourthly, on Linux, the same UID and GID should be used for the replicated files. Fifthly, at the first startup of a mirror module, follow these steps. Start the node with the up-to-date replicated directories as primary using the safekit prim command. Start the other node as secondary using the safekit second command. For subsequent starts, use the safekit start command. Replication is configured in the RFS tag of userconfig.xml as presented in the slide. There is a resource associated with RFS to check if the local node has the up-to-date replicated data. If not, the action is to put the module in the wait state, waiting for the start of the other node to resynchronize its local data. The replicated tag is the main tag where you define the absolute path of a directory to replicate. The read-only mode means that the data cannot be written on the secondary to avoid corruption. Inside the replicated tag, you can define not replicated tags, meaning that some files or subdirectories must not be replicated. In the path of the not replicated tag, set the relative path of files or subdirectories inside the replicated directory. Note that renaming files or subdirectories between not replicated and replicated directories is not supported. Finally, you could duplicate the replicated tag as many times as there are directories to replicate. You can use regular expressions in the not replicated tag, allowing you to specify that you want to replicate all entries in a replicated directory except certain ones, or that you want to replicate only specific entries in a replicated directory. In the first example, you can specify that in the dir1 replicated directory and its subdirectories, you do not want to replicate entries with the extension .tmp or .boc. In the second example, you can specify that in the dir2 replicated directory and its subdirectories, you want to replicate only the entries with a .mdf or .ldf extension. Let's now examine how the real-time file replication works. The first thing to implement is the interception of write access inside replicated files. To do that, SafeKit uses a mini filter in the Windows kernel and a localhost NFS mount on Linux. On Windows, the RFS mini filter intercepts write access requests inside replicated files. Then it forwards them to the local file system. Lastly, the mini filter sends the data to the NFS box process. On Linux, SafeKit begins by mounting the replicated directory on localhost through NFS. The NFS client then intercepts write access and replicated files. The write requests are subsequently sent to the NFS box. Finally, the data is transferred to the local file system for storage. In both cases, the NFS box process will implement the transfer of data to the secondary node. SafeKit implements synchronous replication with no data loss. This means that on a synchronous write I/O requested by the application, it waits for the acknowledgement from the secondary node before acknowledging to the application. Here is an explanation of the use case with async set to none in the RFS tag, meaning that the write I/O must be put on both disks before acknowledging to the application. In the figure, you see that the NFS box process of the primary node sends the replicated data to the NFS box process of the secondary node. Both OK1 and OK2 must be received before acknowledging to the application on the primary node. Each NFS box process retains the last time the nodes were synchronized in terms of replication in the sync timestamp variable. Here is an explanation of the semi-synchronous replication use case, with async set to second in the RFS tag. The only difference is that the NFS box process of the secondary node keeps the data in its cache, sends OK2, and then writes to disk later. In case of a failure on node 1, there is still no data loss. Note that there is still a possibility of data loss in the special case of a simultaneous double power outage of both nodes, with the inability to restart on the former primary node and the requirement to restart on the secondary node. When a node is alone without a secondary, the NFS box retains all modifications made by the application inside replicated files and bitmaps. The goal is to optimize file resynchronization on the secondary node when it is restarted. Note that the bitmaps are activated only after a first successful synchronization between nodes and are deactivated in the event of a crash of the secondary node. Let's examine the process of resynchronizing the secondary node without stopping the application on the primary node. The resynchronization is implemented by the process named reinteger and running on the secondary node. There are three key scenarios to consider. First, there's the entire copy of all files. This is applied at the first start of the secondary node or when using the SafeKit second full sync command. Second, there is the copy of only the modified zone set in bitmaps. This requires a first successful synchronization and a clean stop of the module. On Windows, it also requires the activation of the USN log to work after a reboot. Third, there is the entire copy of files modified since the sync timestamp. It also requires a first successful synchronization. This method is used when the bitmaps are not safe, such as after a node crash, an NFS box exception, or modifications of the replicated directories during a module stop. Let's now examine the different mirror state transitions. Here are the main states of a mirror module. When the state is alone and the color is green on a node, it means a primary server without a secondary. The failover is not possible in this state. When the state is prim and the color is green, it indicates a primary server with a secondary. The failover is possible in this state. When the state is second and the color is green, it signifies a secondary server with a primary. The failover is possible in this state. The stop state means that the module is not running on the node. If the state is second and the color is orange, it means that the node is currently resynchronizing replicated folders. The failover is not possible in this state. When the state is wait, the color is red, and the message is not up to date. It means that the node is waiting for the start of the other node as it does not have up-to-date data. If the state is wait, the color is red, and the message is a failover rule name, it means that the node is waiting for a mandatory resource controlled by a checker before starting. Finally, if the state is error, it means that the console cannot connect to the node because either the node has crashed or there is a communication issue between the console and the node, such as a firewall issue or the web service not running on the node side. Let's consider the start of the up-to-date node 1, which goes from the stop to a lone state. In the figure on the left, when the prim or start command is executed on node 1 in the up-to-date state, the pre-start script is first executed. Normally, the application integrated in the module should not run on the node, but if it is the case, the pre-start script makes a preventive stop of the application before installing the replication mechanisms and the virtual IP address. Then, the start prim script is executed to start the application, and the state is alone orange. After the execution of the start prim script, the module is in the stable alone green state, meaning that the virtual IP is set and the application is running. The module can be put in the wait red state if a resource is set to down by a checker. Now let's consider the stop of the module by an administrator or a checker. In this case, it transitions from the alone state to the stop state after executing the stop prim and post-stop scripts. In this slide, we continue the presentation with the start of node 2, which will become the secondary node. In the figure on the left, when the second or start command is executed on node 2, which is in the not up-to-date state, the pre-start script is first executed. Normally, the application integrated in the module should not run on the node, but if it is the case, the pre-start script makes a preventive stop of the application before installing the replication mechanisms. Then, node 2 resynchronizes replicated files from the primary node and stays in the second orange state during this process, which can take a while depending on the size of data to resynchronize. After the resynchronization, the module goes into the second green stable state, ready to restart the application in the event of a failure of node 1. As shown in the figure in the middle, on node 1, the module transitions from the alone green state to the prim green state once the module is second green on the other node. Let's now consider a stop or a failure of the primary node and the resulting state transitions on the secondary node. In the left figure, we consider the standard use case with the failover attribute set to on. In the event of node 1 failure or stop, node 2 transitions from the second state to the alone state. During the transition, the start prim script is executed in the alone orange state, and when it ends and the application is started, the state changes to alone green. In the middle figure, we consider the special case with the failover attribute set to off, meaning that the administrator does not want an automatic failover on the secondary. In this case, when node 1 experiences a failure or a stop, node 2 transitions from the second green state to the wait red state, waiting for node 1 to restart. If administrators want to force the start as primary on node 2, they can stop the module on node 2 and use the safegitprim command to force the start. Thus, with the failover set to off, the administrator manually controls when the secondary node becomes primary. When there is a stop or failure of the secondary node, the primary node transitions from the prim green state to the alone green state. The application and the virtual IP are not impacted by this transition. Only the replication to the secondary node is stopped. Let's now explain the implications of network isolation between the primary and secondary nodes. When both nodes are isolated, each node transitions to the alone state as all heartbeats are lost. In this situation, the application runs on both nodes, the virtual IP is set on both nodes, and the data is modified locally on each node. Once the isolation is repaired, one node becomes the primary and the other node resynchronizes its data and becomes the secondary. The final status can be either prim second or second prim, according to the duplicate IP address checker. Network isolation occurs when all heartbeats between node 1 and node 2 are lost. As long as there is a live heartbeat on a network, the split brain situation cannot occur. Therefore, implementing an unbreakable private network, such as a direct Ethernet link between both nodes, can avoid this situation. Another way to avoid the alone state is to configure the split brain checker of SafeKit. The split brain checker is explained in the checker slides. Let's now explain the restart action initiated by an administrator or a checker. The restart action consists of executing the stop prim and start prim scripts on a node to restart the application locally without triggering a failover. In the left figure, in the prim case, the state is prim orange during the execution of the stop prim and start prim scripts. In the middle figure, in the alone case, the state is alone orange during the execution of the stop prim and start prim scripts. Let's now talk about the swap action. This action reverses the roles of the primary and secondary nodes. The swap action is equivalent to the stop-start action executed on the primary server. The action can be initiated by an administrator or a checker. As shown in the figure, the application is initially running on node 1, the prim server by initiating a swap or stop-start action on node 1. First, the stop prim script is executed on node 1. During this execution, the state transitions from prim green to prim orange on node 1, during which the application is stopped and the virtual IP is unset. After that, the virtual IP is set on node 2 and the start prim script is executed on node 2, which transitions from second green to a lone green, meaning that the application is restarted on node 2. After the module has stopped on node 1, it automatically restarts and transitions to the second green state after resynchronization of data. Finally, the roles of primary and secondary have been reversed between node 1 and node 2. Thank you for your attention. If you have any questions or need further clarification, please feel free to ask.